I think in the intro we'll kind of cover like we're starting from nothing as far as you don't have any experience with Fusion or machining. Right. At that point we can kind of dive in. Hey folks, we're here with our Hurco. Today Kevin is going to show me, or maybe I'll show Kevin, of how to make a small simple part from idea, concept, quick little drawing on a piece of paper. Then we're going to go to a 3D model, program it all within Fusion 360 and make it on the Hurco. So we're here with Fusion 360 and this is a CAD CAM software that's going to let us design parts and then make them. In the CAD side of Fusion 360, we're going to start by making a sketch. We make a sketch, we select a plane, and then we can sketch a rectangle. We can then push D for dimension and throw some dimensions for where we think we want to be. The real value in CAD software is being able to get a very good visual. So no longer do we have to pull these numbers out of thin air without having any good representation of what they look like. We're able to put them on the screen and get a good visual for how they're going to work together. So after I had that sketch made, I pushed E for extrude, and then within the extrude feature, we're able to make that sketch three-dimensional. We gave it a dimension of 1/4 inch, and now we have a body. So from there, we can add another sketch. We select a plane. We can select any of the construction planes, or we can select a surface on the model that we already have. So we can select this top surface and then draw another rectangle. E again for extrude, and then we can give this some three-dimensional geometry as well. So from there, we can create another sketch and create the hole we need. So we'll start by making a circle. Within extrude, we can either add to the model that we already have, or we can intersect the model and it will cut the body. So now we have a hole. Let's make that an 1/8 inch, and then we'll use a 1/4 inch end mill. So when we use it, it makes the radius that we're looking for. So we can also round these corners to make it look good. There is the option to be able to add a chamfer within Fusion, but I typically don't do that on the modeling side, and it makes life a little bit easier on the CAM side. There's a lot of different ways that we could go about making this. You could attack it from the top and then flip it over and attack it from this side. You can make it this way.
So you're talking about having the raw material clamped in the machine and how you're going to machine it out.
Yes. So starting to think about more of the programming side now. Exactly how we're going to op this part out would be how it's referred to. What operations we're going to do first and how we're going to do them. From this top side, we can only reach so many features with a 3-axis machine. One option would be to machine this top face and then flip it over and machine this. Another option might be to machine this as the top of it at first, flip it over. You would have to clean off what's left in the bottom where you were holding it in a vise, and then set it on its side to drill a hole in it. There's a lot of different ways you could go about it. We'll probably be better off to do it this direction, where we'll machine as many features as we can from this top side, and then we'll flip it over and finish it up. And that way we're getting it done in 2 operations. We can jump over to manufacture, is what Fusion calls their CAM space. On the manufacturer side, the first thing we're going to do is create a setup. So we do so here. Here's where we're going to tell it the work coordinate system. So essentially tell it where machine is referencing 0 from, and then what orientation we're going to set up this part. The default is model orientation, but that is not the way we want to do it. So we're going to select a Z and an X axis. So we can select any line on the part that would represent the Z, and then machine it this way. So we'll machine that. We'll set that as the x-axis, and then we can flip it to where it's where we want. And the next tab of the setup is where we can establish the stock size. So default is a relative size box. We'll start with a fixed size box. We'll just go ahead and cut this one time. So we'll make it 2.88 inches in the X direction. And then we can go ahead and cut it at 1.5 inches in the Y. 99% of the time, you want to try to orient your part to where the longer dimension of the stock is moving in the X, or is in the X-axis, so that way when you clamp against it, you have less material to bow. So if you think, if I was putting this whole chunk in a vise, I would want to program it to where I'm holding it like so, right. Just because holding it like this is going to give more room to bow. Okay. So we need to start out with a roughing operation. In Fusion 360 calls these adaptives. Here in our different toolpath options, we have 2D toolpaths and 3D toolpaths. A 2D toolpath, when it says that, it's essentially talking about Z is going to come to a position and then X and Y is going to move around in whatever shape it needs to contour your part. Whereas a 3D toolpath is for all three axes moving at the same time. So we'll use 3D adaptive clearing, select that end mill, and then since we're working in aluminum, speeds and feeds are pretty forgiving. You have a lot of options for how you can input this. So we can just call it 8,000 RPM. In aluminum, your surface speed is really forgiving. Your feed per tooth or your feed rate needs to be reasonable. I can tell you with a lot of confidence that if we rough this part out at 4,000 feet per tooth, we're going to be doing just fine. Lead in, lead out, that's just coming into the cut, coming out. And then ramp and plunge are only really critical if you're actually cutting in the plunge or if you're going to be ramping into the material. So that would be like if you had a pocket and you need to get down in there. 3D adaptive is going to essentially look at your entire part. You can give it different boundaries. I don't think we need to right here. We should just be able to tell it stock contours, and then we'll tell it some heights on our height tab. Because we're roughing, we want to be able to come down and finish those walls. We want to drop down our bottom height down below that. So we'll go 40,000 below for our roughing tool. Our optimal load here is very important. So an adaptive strategy is creating a toolpath to clear out an area and attempts to keep a constant radial load. General rule of thumb in aluminum, anywhere between 10% and 40% is going to be pretty good of your tool diameter. So we're using a 3/8 inch end mill. If we went a 1/4 inch depth of cut, we're going to be at 93. So we'll call it a 90,000 optimal load. So you'll see when the toolpath is generated a little bit more clearly here what we're talking about. So the roughing step down, maximum roughing step down, is how much length of cut it's going to take in any given pass. We have a 1 inch length of cut end mill that we're doing this with, so we can go much larger than, what was that, 390 it was originally given. Yeah. And then this fine step down is going to be how finely it increments. So that'll be more clear once the toolpath generates. And I'm going to set that at 10 thousandths. And then for a stock to leave, since this is a roughing operation, we're going to leave stock to leave the part a little bit bigger than the final size. So that way a finishing end mill can come through at finishing speeds and feeds and make it look good. So we'll go 6 and 6. 3D adaptive is a very heavy computation to lift. So it takes longer than others, but there is our toolpath. So that fine step down we were talking about, it is how fine these steps are that it's incrementing along, say, a 3D contoured.
Like, what are some things you would look for on that toolpath that may be concerning?
Overall, a common mistake that I'll make is having your stock settings incorrect and or on your heights tab incorrect. So you'll have it in your mind that my adaptive strategy, say, cleared off the top of my part, but sometimes it didn't. So then when the finishing end mill comes back, it's taking a 30 thou pass instead of a 6 thou pass. So one thing I looked at here was just to make sure that that toolpath came around the top. That was the biggest thing, and just to make sure that there's not any overly redundant steps or anything like that. So I can run a simulation and it'll show you exactly what's going to happen. So that's where we are so far. Looking at our different finishing strategies, I can pretty confidently say that 2D contour is the most popular. We can select 2D contour, and we do not want to use the same roughing end mill. So this we will run at 500 surface speed, and we'll give it a feed per tooth of 1 thou. So that's going to come out to 11.4 inches a minute. And then for our contour selection, we can select the lines that represent the path we want the end mill to take. And as long as we give it a bottom height that will allow it to follow that shape, then it'll make it all one consistent toolpath. We can use the same end mill, do a facing operation. We just want to clean off that top surface. We can even use the same speeds and feeds, but we will select that as our stock selection. Then the bottom height is going to come across right at the model top, and we will give it a pass extension of 375 just so it gets off the part. And now that will clean up the top. So all we have left are the hole and chamfer tools. So there's a couple different ways we can go about the hole. So we could drill it to size, but typically drill bits don't leave the best surface finishes. We could just use an end mill and use a boring operation where it'll helix down through there. Or we could drill it undersized first and then come back and finish it with an end mill. There's a lot of different options. If I was going to run 1,000 of these, I would set up a drill bit a little bit smaller than that hole diameter and then drill it and then come in with an end mill just to finish that wall to give it a better surface finish. But since we're only making a couple of these, we'll just do it all with an end mill. And then here is where we can tell it we want to do a finish pass. So that is going to leave stock as it helixes down in there, and so it'll make a smaller helix, and then come back and just do essentially a 2D contour to finish it. So now just a finish pass, or I'm sorry, the chamfer tool, will go about an 1/8 inch, 125 should work well. And actually we'll see here that might be too much. So we'll select a corner as an entry position, and we'll give it a little horizontal lead-in radius just to make it a nice smooth transition into the cut. So nope, it is not too much. So like this is an example where if you put too large of a chamfer tip offset, it would not machine the chamfer on this edge because this flange is in the way. And Fusion's pretty good about not ruining your part with your chamfer tool. So that's op 1, should make a good part. Op 2 is going to be very, very similar, just with a few less operations. The big thing to remember is we're not trying to clear all the material now, we're just trying to clear essentially a hat off the top. So changing the setups, it does that. Control G is generate. We still will need to clear out this area. So what we can do is change our bottom height to represent that. And should just clear. If anything, it might clear too much. We changed our height, and now we need to change our stock contour to let it know what area it needs to clear. So we can select that geometry, hit OK, and it should generate a toolpath. Here we go. So that is what we want. We'll finish the floor, finish that vertical wall. We do not need to finish the outside again. Finish the top, and then we do not need to worry about that bore. We will chamfer the top, chamfer the hole, chamfer the outside edge.
Should make a good part. Cool.
This machine has a probe and is going to help us line up the second operation. We'll use it to set the work coordinate system for op 1 as well, but we don't need to worry too much about making it perfect, running from part to part to part, because everything will be relative to the machine's movement, not to where the stock is placed. We can go over here to the inspection tab, probe work coordinate system. We'll have to tell it that we have a probe.
It is a 6mm probe. What's that in American?
Did you say millimeter?
I know, it hurt my heart.
That is 236. So, and then it is tool 1. Select that. So we can tell it to probe X, like so. We'll hit duplicate and tell it to probe Y. So here it looks like it's probing into space, because it would be if the part was finished. But we're going to do this right after that initial 2D adaptive runs. So when we put the part in the vise, the first thing it's going to do is clear the top off. Then these finished walls will be exposed, and then we can bring the probe in to touch off the part. But since this area has not been cleared out yet, there will still be material there for it to probe. So then it will come down once it precisely knows where the part is and conduct the rest. From here, we select our operation. We can do a final simulation to see that we're making a good part. The final button here says go to the end of the toolpath, and that shows us what we're going to end up with. And then you hide the model itself. So just completely calculated from the stock, that's what you're going to end up with. I do this for almost every single part that I run, because it gives you a visual of what the toolpaths are actually creating, not what you hope they're creating. This is a good way, and the most common place to catch mistakes. We need to post this program. So that's where the software is going to actually create a G&M code. Select that setup, we'll hit post, and then the software needs a post processor to do that. Right now, the post processors that we need are on the flash drive. We're going to be running this on our Hurco, so we need the Hurco post processor, and then these settings all default back. So now we can hit post, it goes to the flash drive, we'll hit save. So let's fire up the machine.
So we just fired up the machine. The only thing we've done so far is flip the switch on the back. Now, this machine does not have a vise on the table. We're running wheels, we don't use vices for those. We need to throw a vise up there to be able to make these little parts. And then we'll blow it off with an air gun. We should put glasses on before we do that.
All right, camera person, bring your glasses.
So that goes like so. So we get it good and tight, and then we'll smack with a hammer, feed it down, input parallel, nice and tight. So we're gonna have you dog the probe down where it's sitting right out here, and then we'll go from there. We need to get a part set up on the option.
And now work offsets. We just need to hit start probing cycle and then cycle start.
So now our work coordinate system is set. We're ready to start the program.
Now the machine knows exactly where the material is and where the program is going to go.
Oh yeah, we're good. so good. Cool. There's the first side done.
So here we have our finished parts. I know I learned a lot during this process, and in case you're wondering, these are intended to be welded onto the bottom side of a swing arm so that a motorcycle rear stand can go through these holes and lift the back end of the motorcycle up.
So thanks for watching. Hopefully you guys learned something too. If you like the video, give it a thumbs up, subscribe. If there's anything we can do to help, reach out to us. So thanks, take care out there, and remember, when in doubt, gas it.